So James Steer is going to give this talk, and he's actually first author. So please, James, go ahead.
Yeah, thanks very much, Henrik. So I'll be presenting some of the work on breaking wave impacts that we've done on smart boulders. So we've carried this out with colleagues Olivier Camoun in Marseille. And we've just completed experiments earlier this year, although we were supposed to start last year, but of course that didn't happen. So I'll start off with a bit of background on the project and some of the work that was done before I joined HiWave. So Rona Cox, who's a geologist, published some papers, as well as Frederick, on the multi-wave ERC project. And these were sort of concerned with nonlinear dispersion and the amplification of wave run-up. So this was a number of years ago, but sort of resulted in a campaign of it was primarily sort of concerned with storm waves and storm waves impacts on boulders, because for a long time there have been sort of controversy in the movement of large boulders and whether these movements are due to tsunami or whether they're due to storms. And quite recent work by Rona Cox and Frederick, as well as Andrew Kennedy and others, have sort of been reevaluating some of the boulder movements that were recently thought to be caused by tsunamis and looking at whether they could have actually been caused by storm waves. So this year, one of the papers down below with Andrew Kennedy kind of looked at the different sizes and elevations and the distance inland of different boulders, and came up with a dimensionless sort of analysis of whether they were moved by storm waves. So previous studies thought they'd be moved by tsunami because the predicted significant wave height would have been unbelievably large for a storm wave. So people concluded it was tsunami, but we're now kind of rethinking that. So the sort of scales that we're looking at here of the boulders, here we can see the Uden-Wentworth grain scale, which at the upper limit on this slide goes up to 4,000 millimeters, where we just start to call things boulders. And then it also goes to very fine scales like clay and silt. But our, so there it's sort of parameterized by this phi value, which is d is the diameter of the grain, and d0 is just a 1 millimeter grain. So the boulders that we are interested in are kind of here on the 4 meter scale, so extremely large, extremely heavy boulders, but of course this scale goes all the way up to the kilometer scale. So this is the sort of scale we're looking at, very, very coarse boulders, very fine blocks. So coastal boulder deposits. This image, I believe, is, well, it's certainly on the west coast of Ireland, and I believe is on one of the Aran Islands, possibly, yeah, one of the Aran Islands. But here we can see that it's very, very steep cliffs, sheer cliffs, the very angular kind of construction with these large boulder deposits on the top. And one of the things that we can see is that there is this area from the cliff edge backwards clear of boulders, where we can imagine that boulders have been essentially quarried from the cliff and then moved backwards due to storm waves. And often you find mega gravel within this, within these boulder deposits. Okay, yeah. So as I said, that picture was taken, I think, on the Aran Islands, which are made up of 3 islands on the west coast of Ireland. So you have Inishmore, which is the largest, Inishman, and Inisheer. And these have some of the best developed coastal boulder deposits. And this is the sort of geographic location where all of the work that I'll talk about has been carried out. So why do the Aran Islands have such boulder deposits? Well, they're constantly hit by Atlantic storms and occasionally the remains of hurricanes. It's a very energetic coastline. The boulders that we saw on top of the cliff, yeah, so they're normally quarried from the cliff edge by sort of hydraulic action. So you can see here one of the largest boulders can be removed from a cliff collapse. There's a lot of overhanging cliff on the Aran Islands. So before I joined UCD in the winter of 2013 and 2014, there was a very energetic winter in Ireland where the west coast was struck by a number of depressions, a number of storms, and the waves were continuous throughout the winter. So this on the left here is an image taken in this winter, so 1st of February 2014, is a 30-meter high cliff being struck by a wave. So you can really get an idea for what's going on in the energy just of this coastline. And a HS of 19 meters, which is just incredible. So during this winter, there was a campaign of recording. Prior to the winter of 2013-2014, there was a campaign of marking where some of the largest boulders were on the west coast of Ireland, and with an idea to then go back and see whether they'd moved. So this is one of the largest boulders that they looked at. It's a 620-ton boulder, which, following the winter, was seen to have moved 73 meters inland, which it was essentially sort of pretty concrete evidence that these boulders can be moved by storm waves and not just by tsunami. And here we can see a picture of the boulder before the winter and then afterwards. So there was the winter campaign, which looked at real boulders, and the team then carried out some 1 in 100 scaled experiments whereby real rocks were placed on a vertical platform at Queen's University Belfast, and an irregular sea was created, and the wave impacts were recorded with a video camera. These are all fruit scale experiments. So at 1 in 100, we have 1 centimeter is 1 meter and 1 gram is 1 ton. So we have a 453 gram or a 453 ton boulder. And these waves, when you look at the video recordings, the boulders were moved quite a significant difference by these waves. And here we have a 744-ton boulder. But the shape of the boulder, the shape of the crest, the shape of the wave seems to be very important in moving these boulders, which is something that we then looked at in our own lab experiments in Marseille. So I'll now get to where I joined the project. And so as a postdoc, my role in the project was to carry out some laboratory experiments in Marseille to investigate the effect of a breaking wave crest on these boulders. So first of all, we sort of decided on the mass of our boulder. So we looked at the boulders that were recorded during this 2013-2014 storm. So here is a normalized PDF of the masses on a log scale. So on the right-hand side, you can see the dotted line, which is where our boulder would lie if it was in the real world, so scaled up. And we assume a 1 in 30 scaling for that. So it lies very close to a boulder, which was boulder 261, which was in the top, I think it was one of the top 3 massive boulders that Cox et al. Recorded. So we're really looking at the extreme end of this, the boulder's masses. So our aim in our experiments was to primarily look at crest shape and the sea state and look at the relative importance of these parameters in moving extremely large boulders. So the question really is, if you have a wave that focuses at just the right place on a cliff or on a boulder, will it move a boulder? Is that more important than the sort of deep water sea state which created the wave? So the method that we were going to use for this was to use a flume to send a focused wave group towards a vertical platform with a boulder sitting atop it, and then to alter the breaking position to essentially change the breaking crest shape. So to look at waves that had already broken, waves that were breaking, and then waves that were completely unbroken. And so some of the novelty that comes from this is that we wanted to embed our boulder with accelerometers and a pressure transducer. Okay, so the experimental setup. So on the left, we have an idea for what the flume looked like. So we have a set of wave gauges which measured the sort of the global fluid flow and what the waves look like. So you can see that at gauge 1, we have a chirped kind of wave packet, which then focuses at gauge 6 and creates a single breaking crest. The flume was about 11.5 meters long, and the platform height was around 1/4 meter, with the depth being 3/4 meter. So the boulder then on the right, so the right schematic shows the internal equipment that we had inside our boulder. So we have a pressure transducer on the front face of the boulder and 3 linear accelerometers, which were shock accelerometers with very high sampling rate and a very high acceleration range. And then this was all, the data from those 4 instruments was collected by the data acquisition system, wireless data acquisition system, and transferred wirelessly to the PC. So the internal equipment constrained our experiments quite a lot. We barely fit everything in, but the boulder was around 8 kilograms, which actually feels a lot heavier than I thought it would. And so our experimental campaign that we carried out in February, which I'll show our results from, was a bit of a preliminary sort of test to see whether the boulder would move at all, because although we know that these boulders should move and that they do on the Aran Islands, there are lots of errors involved in the scaling. So actually knowing whether it would move or not was an interesting question. So I'll show a video from one of the tests. So on the left, we have this breaking wave coming in, and the black box is our boulder. It's sitting flush with the edge of the cliff, and you can just about see the hole for the pressure transducer, which is in the center of the front face. So we have an overturning crest, which sort of falls into our braking range. Yeah, and we can see that the boulder did move a couple of centimeters. I'll just play that again. And essentially we use the same braking wave, but just with a different focus position to change the crest shape. So I have here some snapshots from 3 tests that we ran. So I'll start at the top where we have test 49. So this had a focus position well in front of the boulder. So you can see in the very top left image, the wave has overturned, the crest has struck the preceding trough, and it's fully kind of broken really. It's very aerated, and yeah, there's lots of bubble entrainment. So that's our kind of broken or aerated state. And then the middle row shows test 8. Sorry, I should say that going from left to right, there's a delta T of 30 milliseconds. So in the middle row, test 8, where the focus position is more or less on the platform. You can see, so this is very similar to the video that I showed. You can see that although the wave is overturned, it hasn't, the crest hasn't connected with the trough yet. And we can see here the sort of slightly less aeration. But when we sort of get to the wave actually breaking on the vertical platform, very small amounts of sort of changing the focus position, a very small amount can change the pressures involved and the type of impact by a great deal. So this test 8, the boulder moved by 38 millimeters, whereas in the previous test 49, it moved by 12. And then test 45, where this is almost a sloshing type impact. So the wave is not, doesn't really have a vertical face until it gets to the boulder. And this was where the wave was focused about 22 centimeters after the platform. So it's a sort of a theoretical focusing position. And there the boulder moved by 11 millimeters. Okay. Okay, so the main kind of figure result from these tests is this, in which we show the change in the focus position on the x-axis and the amount that the boulder moved, delta x, in millimeters on the y-axis. The data points are colored by the amount that the boulder moved. So this figure can almost be used as a type of legend for the rest of the figures that I'll show. So we've broken up the focus position into 3 sections using the dashed lines. So on the far left, we have waves that were clearly broken at the time of impact. Oh gosh, yeah, I'm sort of running out of time, I think. Yeah, so the left section is waves that were broken, then the middle section is breaking, and on the right are unbroken waves or sloshing waves. So we saw boulder displacement for every test that we ran, even some of the ones where we didn't, where the data wasn't recorded properly, or yeah, or the results weren't presented for some reason. So for every test, we found that the boulder moved. So the sort of spectral energy that we were moving, that we were using, really was quite high. Okay, so on the left, well, here we have a figure of essentially the pressures that were measured by the front face of the boulder. So I'll talk you through this and start at the bottom of the figure where we have test 49. So on the x-axis, we have the time, and on the y-axis, we have pressure and acceleration. So the pressure line is gray and it's filled, So in test 49, it's the turquoise, it's filled with a turquoise color because it didn't move very far. And here, the error bars give us a characteristic time of the impact. So it's quite a long time scale impact, although, I mean, it's still only, say, 15 milliseconds. But that is longer than a lot of the other tests. So that was test 49, and then moving up to test 47, we can see that the characteristic time of the impact has shortened significantly. And this is now where we're into this braking region that I was talking about. So we then, in test 47, we have higher pressures, higher accelerations, and slightly more movement. And then moving up to test 56, we then get an increasing characteristic time as we are moving the focus position. Yeah, sorry, so if I didn't say, the plots are translated vertically by their focus position. So in the very lowest one, it's a wave that is braking at 0.6 meters before the cliff. So as we increase the focus position from test 47 up to test around 51 or 52, we get there's increasing in characteristic time, an increase in the peak pressure, and we get these sort of double peaks in pressure where the crest strikes the boulder and then the bulk of the wave, and then there's a bit of air entrainment and then the bulk of the wave strikes it. And this is perhaps most clear in tests 14 and test 8, where we can see that the pressure really is quite high and the characteristic time is quite low. It's a very short, sudden shock type impact. Test 8 is also, it's colored in black because it moved by one of the most amounts. Then continuing up XF to test 21 and test 35, we keep getting an increase in the maximum pressure and a shortening of the characteristic time. And so we're starting to find flip through impacts where the crest and the trough of the braking wave are striking the same place on the boulder. And this then comes to a very sharp end at test 43, where we suddenly get a very long type of impact. We do have a very high pressure peak on test 43, but this is like one data point, and the rest is just a very long kind of pressure measurement. So then test 45 doesn't even have that high pressure measurement at all. But so within this braking region, which kind of goes from test 43 at minus 0.3 up to around test 40 at positive 0.1, we can see a changing in the type of impact that occurs, and we can see this kind of flip through impact. What this means for the so what this means then for the amount that the boulder moved is quite interesting, because what I have here is the same type of plot, but for completely repeated tests. So all of the tests here were nominally the same input parameters. And although they show very similar pressure time histories and acceleration time histories, the amount that the boulder moved actually varies quite a lot. So you can see test 13 there is colored by the light yellow, and test 21 is a dark red. So there's quite a lot of variability in the amount the boulder moved, even though pressure time histories are very similar. So to conclude, so boulder displacements we saw in all of the tests, and we saw a variety of pressure profiles, including a flip through events, very focused events. And our future work will be to alter the C parameters rather than just the focusing positions. And we're also working with Ji in Cardiff, who is looking at building a numerical wave tank of the experiments. I'll let this run quickly if I may, but please stop me, Henrik, if I'm over.
Yeah, well, very good. Thank you very much. Very nice talk, James. Are there any questions from the audience?
Hi, This is Francesco Fedele from Georgia Tech. A very, very interesting experiment and research. I want to ask you something. I noticed that in one of in your experiment, once the wave impacts on the boulder, on the top of the boulder, there is a sort of formation of a wake, which I wonder could create a sort of lift up, which is going to reduce, the weight, and there will be less friction. So I wonder how important. There could be. It's the same as when you have a wind that is blowing over your roof. So it's gonna. Do you think there could be also some contribution from this lift up that is gonna,
Yeah, it's something I certainly wouldn't rule out. And what I would say is that lifting of the boulder is potentially very important because, as you say, it's going to change the friction characteristics, and getting any amount of water underneath the boulder is going to make it a lot more slippery than a dry surface. So when I looked at the results from the experiments, there wasn't any clear indication that, because we do have a Z accelerometer in there, so there wasn't a clear indication that boulder lift up was important to the amount the boulder moved, but that's really something I have to look at again. In terms of actually the wake and whether that causes the boulder to lift, I really wouldn't be able to say. It's a very interesting point. Perhaps could be achieved using pressure transducers on the top face of the boulder.
Of course, I mean, when the wave then slam on the boulder, then it's gonna stabilize the boulder. After the other things is that, did you consider the three-dimensionality of the wave? Here you have only two-dimensional waves. In real, on the coast, I mean, refraction is gonna make waves to attack orthogonal to the coast, but the energy can still spread directionally. So I mean, the front of the crest is gonna be more triangular than a rectangular crest. So, and that will reduce the impact. So I mean, these are all I guess these are all upper bound results, is right? So in realistic conditions, so maybe the effect will be less accentuated. I wonder how you're gonna account for that. I mean, you have any plan for that?
Absolutely. So we don't have a plan necessarily directly for that. I think so. Maybe I can just quickly give this a slide, which so Frederick actually, and along with Ton van den Bremer at Oxford University, are looking for postdocs and who will be looking at crossing breaking waves. And I don't know if that has an application to boulders or not, but that certainly will look into three-dimensionality. For us, I won't be taking into account the three-dimensionality of the waves, or at least not experimentally. It's possible that with Gijwa, we can use his numerical wave tank to look at three-dimensionality. Yes.
Thank you. Thank you.
Okay, we just have one more minute. Here's a question from the audience, which was put in the chat. So let me read it up. This is by Syed Ahmad Hassan. How does the pressure impact compare if boulder is completely fixed?
Yeah, so that's that's a really interesting question, and I can't say definitively. What I will say is that the sort of the flip through impacts that we see where the pressures are the highest do look very similar to previous experiments where people have had a fixed vertical structure and measure the pressure there. I'll also say that in our upcoming experiments, we hope to have pressure sensors on the vertical cliff as well, so that we can, because it's interesting because the there's this coupling, I guess, between the boulder moving and the pressure. So in order to answer your question, we will be putting pressure sensors on a vertical cliff, which won't be moving. So hopefully we'll be able to compare what we measure on the cliff with what we measure on the boulder.
Okay, that's it will be interesting to see. Yeah. So okay, thank you very much for the talk, James.